For decades, humanity pointed massive arrays of metal at the sky, waiting for a phone call. We built dishes so large they had to be carved into the sides of mountains, all to catch the faintest whisper traveling across the void. But year after year, those dishes record the same thing: static. The universe remains entirely silent. Waiting for someone to broadcast their existence hasn't worked. If we want to know whether we are alone, we have to stop passively listening and start physically exploring. This means deploying actual hardware. We're pushing a mechanical frontier outward, starting with the dirt next door, scaling up to systems light years away. Modern missions map the solar system as a series of specific chemical laboratories, prioritizing the search for raw biological evidence over radio signals. The most accessible laboratory is Mars. Billions of years ago, it had liquid water, a thick atmosphere, and active geology, the baseline conditions necessary for biology. To test that history, we've dropped multi-ton nuclear-powered rovers onto its surface to drill directly into the crust. They grind up ancient lake beds, bake the soil, and run chemical analyses to detect biosignatures. These are specific molecular patterns, or fossilized structural markers, left behind by ancient microbes. Our decades on Mars dictate a reset in our expectations. If biology exists in our immediate neighborhood, it likely won't be building cities on the surface. It will be microscopic, and it will be surviving deep underground. That realization pushes our search past the rocky inner planets, out toward the gas giants. Here, on moons like Saturn's Enceladus, we see active geysers. This image shows massive plumes of water vapor and ice erupting straight out of the moon's southern pole into the vacuum of space. This occurs due to tidal heating. The immense gravity of a planet like Saturn constantly stretches and flexes the moon's rocky core. That friction generates intense heat, maintaining churning oceans of liquid water beneath miles of solid ice. Where there is liquid water and a heat source, chemistry can organize into biology. Europa and Enceladus prove that pitch-black, freezing environments can still host active oceans, making them prime targets for living ecosystems. Then there is Titan, Saturn's largest moon. Unlike almost every other moon we've observed, Titan is completely shrouded in a dense, opaque atmosphere. Because its air is 4 times denser than Earth's, we can actually fly through it. Upcoming missions are deploying autonomous drones to navigate this haze and survey the extreme terrain below. What they will fly over are lakes and rivers composed entirely of liquid methane and ethane. Titan is a world rich in complex carbon-based chemistry interacting at temperatures hundreds of degrees below zero. Titan forces astrobiologists to consider biology without water. If microbes can evolve in liquid methane, then the strict rules we thought governed life are just local suggestions, vastly expanding the habitable map of the universe. To grasp that scale, we look beyond our sun. This diagram illustrates the habitable zone, the orbital distance where a planet maintains liquid water. We've identified thousands of candidates. Worlds like TRAPPIST-1e, Kepler 452b, and K2-18b sit perfectly within these zones, presenting vast new targets. We can't see most of these planets directly. We find them by staring at stars and measuring the microscopic dip in light that happens when a planet passes across the star's face. With billions of these rocky worlds in our galaxy alone, the staggering volume of candidates shifts the search to a matter of identifying the right coordinates at the right time. Yet beneath all the data and the math sits a stark reality. The cosmos is mostly an endless expanse of hard radiation, toxic atmospheres, and frozen rock. We look outward to find the specific conditions that produce a world like ours, the only place we have found where liquid water, a stable atmosphere, and complex biology coexist. We have built colossal radio arrays, driven rovers across Martian deserts, flown atmospheric drones, and cataloged thousands of distant stars. After all that effort, we have confirmed exactly one specific location capable of sustaining us. Astrobiology is inherently a mirror. By cataloging the dead, silent, and extreme environments of space, we accurately measure the overwhelming unlikelihood of our own existence. The hunt for alien biology will continue to push our technological boundaries, but the greatest insight from exploring the stars is realizing the fragility of the ground beneath our feet.